Hello and welcome to Bio 214 Introduction to Exercise Science. This is the first lecture in the course, and so we're going to sort of lay out the groundwork for what exercise science is. One caveat as we start, I tend to interchangeably use exercise science and exercise physiology. That will work for this course because I'm taking a very much physiological approach to exercise science. However, exercise science incorporates more than just exercise physiology, and we will be covering those other aspects as well. So if you see exercise physiology within this lecture, you can also easily just think of it as exercise science as well. So with that caveat out of the way, let's begin. So an understanding of exercise science these days is pretty much essential for those aiming to lead a healthy and active lifestyle. But it also has important applications in healthcare, in sports, rehabilitation from injury and disease, and of course in this day and age, wellness programs. So this first module is going to cover the fundamentals of exercise science and physiology and its historical context. And we're going to look a little bit more at the physiology. So we're going to use exercise physiology instead of science in this lecture. And then we'll expand out from there as the weeks go by. So exercise science evaluates how our bodies respond to physical activity, exercise, and training. These are actually, believe it or not, different from each other. We look at how we respond by analyzing both physiological, chemical, and molecular mechanisms which are taking place. So hopefully by the end of this first module, you'll be able to look at the historical development of exercise science and physiology as a discipline, be able to explain the significance of exercise physiology in promoting health and fitness, and be able to define the scope of exercise physiology and its research areas, and describe the applications of exercise physiology within healthcare. And as I said at the start, this will be our most interesting point, the role of exercise physiology in enhancing sports performance. So, the basics of exercise science. Well, exercise science essentially examines physiological and metabolic responses to the physical activity and exercise that we perform. In order to understand physiology and metabolic responses, you need to understand basic science, so biology, chemistry, physics, and maths. The field has numerous practical applications, and so once someone trained in exercise science are able to create exercise programs, not just for themselves or other individuals, but also for athletes. Someone with exercise science knowledge will be able to better help someone prevent and manage chronic disease, and also those that are in rehabilitation from injury or chronic disease to improve their overall quality of life. In the diagram, there's a brief summary of the different fields that exercise science majors can enter into. Very commonly, people with exercise science majors move into the sports arena, so they become fitness trainers, athletic trainers, exercise physiologists, physical education teachers. But these days you'll also see people with this knowledge moving into the marketing area for sports or recreational therapy, and of course the huge growing area of health and wellness product development. But if you want to continue on studying after exercise science as your first degree, you can become a physical therapist or an occupational therapist, or move on into medicine and become a sports medicine physician, which is, if I'm honest, something I would like to have done if I had my time again. It was kind of how I got involved in everything to start with. I came through sports, became interested in medicine, and then from there back into the exercise science. Anyway, so other potential jobs, well, coaching of all different types. Obviously strength and conditioning coaching, but just standard coaching for various sporting fields. And this is by no means an exhaustive list. There's many other areas that someone qualified an exercise science major can take up as a job. So we teach these courses as conceptually, meaning that we talk about one particular idea at a time. And at the 200 level, we kind of leave the ideas separated from each other. So we like concept 1, concept 2, concept 3. And as you move to 300 and 400 level classes, which of course have more detailed information, we pick those concepts back up and we go into more detail with those concepts, and then we start showing how they actually link together. And by the time you graduate with a bachelor's, for example, the idea is that you have a wide understanding of the area and how it interrelates. And if you move past, graduate or undergraduate learning and into the postgraduate field, then you'll start looking at the wider picture even more, or going very specialized and going to a greater detail. But we'll start with the concepts and build on those. And in order to understand those concepts, you really need to understand the terminology being used. Now, within science generally, that can actually become a barrier to learning and just make things slower and harder. So I focus on terminology as a result of that. Why is terminology a barrier? Because the terms tend to be in Latin. Latin is a dead language, meaning that once you name something with a Latin name, it's not going to change, because dead languages, of course, do not evolve. Whereas the language we're speaking now, which is English, changes all of the time. Words modify over time. Gradually, there's many examples where something actually, like in recent colloquial English, people started using the word sick, meaning good, meaning amazing, meaning that's really cool, as opposed to sick meaning, well, you need to go and see a doctor or maybe be admitted to the hospital. The same word used in entirely different context. So we use the dead language because the name, once we name something, isn't going to change, and therefore everyone has a quick understanding of what's being said. And I'll give you an example of that. Physiology, which we're going to focus on in this course in the context of exercise, is basically pinned around maintaining homeostasis, which literally translates into English as same state. So the body is trying to stay in its same state, which is a state of health. And we have feedback mechanisms which allow that to happen. If one of those feedback mechanisms starts to malfunction, then you move out of same state and you enter a disease process, which is when we try and convert it back to that same state, or mask it or modify it using medications. So homeostasis, for most people on the street, is, I don't know what that means, I have no idea what you're talking about. So if we begin to break these words down and understand what they are, when you think homeostasis, you think same state, immediately you have the basic understanding to move forward. So terminology to me is important, and I have always built into my courses a match-up boxes in the study area, which are not graded, but they help you practice and get used to the terms, which will then be tested for grade in the midterm and in the end of term exams. So it's always useful learning these things as you go, because it becomes much easier. It's 25% of each of the exams will be given to just understanding and matching up terms. So I do pay a lot of attention to it, and I encourage you to as well. So anyway, so familiarity with key concepts and terminology is crucial in the study of exercise science. So what are they? Well, exercise physiology. Exercise physiology is literally how the body responds to physical activity. I mean, the physical activity is being interchanged with exercise here. Physical activity itself is just planned, structured, and repetitive movements which are aimed at improving or maintaining your physical fitness. So what is physical fitness? Well, physical fitness is a collection of attributes that enable an individual to perform physical activities, including cardiovascular fitness, muscular endurance, muscular strength, flexibility, and even body composition. So I'm going to take a minute or two just to talk about this, because whilst these three terms are very basic, very simple, if you understand these three terms, you basically understand everything that we're going to cover in this course. So let's flip it and talk about physical fitness. What is physical fitness? Well, we just said it's a collection of attributes that enable individuals to do cardio, strength training, muscular endurance, move around, be flexible, maintain their body composition. And that doesn't mean how they look in a mirror. That means the appropriate level of fat, appropriate level of protein, so that they can have the muscular strength, etc. Physical fitness for one individual to another individual can be very, very different. And that's where understanding so much of the other aspects becomes important. If you have in front of you a 17-year-old individual who has been very successful in sprints, for example, since they started a middle school to high school, and they want to improve and maybe go to states or go even further, their physical fitness is going to be incredibly different to someone over the age of 65 who is post-heart attack. But they'll both have physical fitness goals. The physical fitness for the young individual who's sprinting is to develop the muscles to become stronger to allow them to sprint faster. Their muscular endurance isn't in a sprint very important because most of their work will be anaerobic, meaning they don't need that endurance. They just need enough energy within the muscles to take them all the way through the sprint itself. And the more energy they're storing and the stronger those muscles, the better they will be. So that would be their goal. That would be what you plan for them. Cardiovascular fitness is, again, not very important to them. However, if they're sitting next to someone who is the same age but is a long distance runner, then cardiovascular fitness and muscular endurance become extremely important, and muscular strength takes a back seat in comparative. If you have a gymnast sitting next to them at the same age, then flexibility, muscular strength is going to become much more important. So these are all physical fitness goals for individuals. For that elderly person post-heart attack, their physical fitness goals can be going home where they live alone, but to be safe and to be able to continue to do so. So just to be able to get through their each day and do all the things that they need to do, like getting dressed, washing themselves, going shopping, being able to make food, basic parts of life. So physical fitness for different individuals can look very different, but it's important for every single individual, living on this planet. Physical fitness is a real thing. So in general, physical fitness is just, are you fit enough to live your life, whatever that life entails? So how do we maintain physical fitness? Well, we take part in physical activities, and these are the planned, structured, repetitive movements aimed at improving or maintaining your physical fitness. So again, that's going to look very different, as I just mentioned. You're going to do strength training if you want to be a sprinter. You're going to do cardiovascular training and muscular endurance training if you want to be a long distance runner. You're going to do flexibility and muscular strength. You want to be a gymnast, for example. For someone who's post-heart attack in their mid to late 60s, body composition suddenly becomes important. You might be carrying too much fat in the abdominal cavity, and that needs to be reduced because it's putting pressure on your heart and your other organs. So physical activity needs to be planned around the physical fitness goal. So why exercise physiology then? Why just come up with a plan, for someone who wants to run faster? It's like, well, we need to understand how the body responds to the actual physical activity. We need to understand, for example, if you want to improve long distance running or improve sprint running, you need to actually look at the muscles themselves. And the first thing you want to know is what percentage of what type of fast or slow twitch fiber is in that individual's genetic makeup and in their muscles. Because as we train, we can encourage intermediate fibers to, take up some of the extra work, which allows someone to be to run longer. But at the same time, we start with a genetic component, and then we try and train to improve that genetic component up. So if you have a lot of slow twitch fibers, you're going to naturally be a better endurance athlete than you are going to be a sprint athlete. But if you have a lot of fast twitch fibers and you develop them, then of course you're going to have explosive strength and you're going to be able to sprint faster. But understanding these things is something that we're going to look at in this course, is going to help us develop physical activity plans that's going to make that physical fitness for that particular goal work. So, continuing the concepts and terminology, we have a few other things just to mention before we move on. Aerobic exercise versus anaerobic exercise. Aerobic means using oxygen. Oxygen is used to generate energy, and a lot of it quickly from glucose at high energy output activities, or fatty acids at general day-to-day moving around energy requirements. So aerobic exercise tends to be those things that we're quite commonly associated with as jogging, cycling, swimming, etc. Whilst we can produce a lot of energy using oxygen, it takes time to do that, but it's very good for endurance. Anaerobic exercise does not require oxygen for energy production. Therefore, it's not good for endurance, but it can give you an intense burst of effort. And so obviously someone that's doing clean and jerk in weightlifting, lifting huge amounts of weight above their head, or as weightlifters have to do clean and jerk in the snatch, they need huge amounts of anaerobic strength, meaning that their muscles have to be able to generate huge amounts of force very quickly to move that weight from the ground above there and then hold it above their head and lock their arms. Sprinters, same. Jumpers, the same. They've got to be able to generate force quickly. They don't need to do it for long. So anaerobic exercise becomes important for them. So that's things like strength training. Concept that we will look at in more detail in this course is the VO2 max, the maximum volume of oxygen. So this is the absolute top amount of oxygen we can take into our bodies to basically maintain an endurance or cardiovascular activity. As we train cardiovascularly, our VO2 max can increase, and if you look at the natural VO2 maxes of the world's top athletes, their numbers are incredibly high and more than double of someone just walking down the street who's otherwise generally physically quite fit. And metabolism. Now, metabolism is something that we use in day-to-day conversation, but it's often kind of like misused. So metabolism, the chemical reactions in the body that convert food into energy and other molecules required for life, and this happens at the cellular level, and essentially we're producing ATP energy from it, and then we're producing the proteins to maintain the structure of the cells, etc. So that's concepts and terminology. So exercise science has grown out of other scientific disciplines, and these essentially are physiology, biochemistry, and biomechanics. So the integration of physiology, which is the study of the functions and mechanisms of living organisms, that maintenance of homeostasis, what is normal for each of the organ systems to do and how they do it. Biochemistry is at the cellular level, and this is the chemical processes which are being used and then changed and then modified into new chemicals to maintain the function of the cells which support the tissues, organs, and organ systems. So biochemistry underpins physiology. Biomechanics is the analysis of the mechanical principles that govern human movement. So the kinetics, the physics of it. So as you see in the diagram there, there's three people about to lift a weight off the ground. It's a free weight, and one of the things I hope to be able to get into is the difference between the free weight, use of free weights and the use of weight machines. Both have their role with training, but free weight requires proper technique and safe technique, and so biomechanics is the most efficient use of the body's movements to maintain or to carry out a particular action. And the more efficiently you can do that, the better you will do it. So for example, think of throwing a javelin, something I will talk about in the future of the course, because coming from the UK, we had a world champion back in the 80s and early 90s who almost rarely threw the javelin because of so many injuries to his shoulder. but at the same time was able to use things like sports psychology and mental training and very specific biomechanical training to maintain his ability to compete at the highest level and still break world records. So, as I said, we'll take the javelin. The movement of throwing a javelin, some of you may have done that in your own lives, is very, very exact. The biomechanical mechanisms for that, the more efficiently you can set your body up at the moment of release, having built up a lot of potential kinetic energy, and then release the javelin smoothly from that practically stationary position, generates so much force into the javelin itself that it flies further. The more efficiently you can do that biomechanically, the further that javelin will go. So that's why that adds itself particularly well into the sporting arena. So other things that contribute to exercise science. Unsurprisingly, nutrition. Obviously, nutrition and the exploration between the relationship of food, nutrients, and health has been known really since the 1980s as being absolutely key to sporting performance, but also just for general wellness in life. And as we also know, we are having issues within the developed world of basically an epidemic of diabetes type 2, which is a nutritionally triggered disease. So being able to access and eat the right foods for your particular needs is very important. Psychology, as I mentioned before with the British javelin thrower, the study of human behavior and mental processes, we can use sports psychology in particular in different ways. One, it's the mental toughness to keep going under extreme amounts of pressure. Secondly, we can use it to train the mind because the mind controls the body. So you can actually go through movements in your mind. You can think yourself through them. And by doing so, you're actually strengthening the connection between your brain and the muscles that it's going to control in those movements. So it actually allows you to train without actually physically moving. Medicine. Obviously, the branch of science focuses on diagnosing, treating, and preventing disease, and that comes into all walks of life, obviously, and exercise science is one of them. So being able to help someone that's developed a disease, we can use exercise science to mitigate some of the worst aspects of maintaining their strength so that they recover faster, they can maintain their physical fitness for what they need to do, etc. And a very closely related field is sports science. This is an interdisciplinary field that combines insights from multiple scientific areas to enhance athletic performance in particular, and also to prevent injury. So it's a subset of exercise science. And it's actually where I go into this, because when I did physiology when I was at college, it was human physiology and sports science. And so that was my entryway into this fascinating subject. So to finish this lecture, we'll have a brief look at the history of exercise science, and I do mean brief, this isn't a long one. So, exercise science examines how the body responds to physical activity, as we've said, and has a very rich history that dates all the way back to ancient Greece, where athletes trained in gymnasiums to enhance their physical fitness. Modern study of exercise science didn't begin until the late 19th century, with the advent of laboratory techniques designed to measure the body's physical responses to exercise. So back in the 1920s, researchers focused on metabolic processes, while the 1940s saw significant studies on cardiovascular health. And that actually was dovetailed with the fact that in the 1940s and the 1950s, we had an issue where middle-aged men in particular in America were suffering heart attacks, and we wanted to understand why. So the 1950s and 60s brought investigations into muscle physiology and resistance training, and then from the 1970s onwards, research expanded to encompass other body systems such as our immune systems, our endocrine systems, and technological advancements led to a much deeper understanding of the molecular mechanisms that govern the body's response to exercise. And of course, that continues on. So, there's been a number of people associated with advancing our study of exercise science, and particularly exercise physiology. And there's a lot, so I've only just picked a few. This lecture was developed from another existing course, so I have to thank them for that, and I will do in the at the end of the lecture in the back on the actual course main page. So A.V. Hill developed techniques for measuring oxygen uptake during exercise, which really opened the door to understand how our oxygen demand increased over, as we exercised, and exercise performance was modified depending on how good or how well we could do so. August Crowe created methods for assessing blood flow and capillary circulation regulation. Massively important, because obviously the blood is carrying the oxygen to the body so that the body can, so the cells can make energy. Peter Pedalfast made significant strides in understanding cardiovascular respiratory function during exercise. Kenneth Cooper was well known for popularizing the concept of aerobic exercise to the population as a whole. And so their work has led to discoveries such as lactate threshold, we'll talk about, the role of glycogen and muscle energy, to kind of show you a little bit in the diagram, and identification of genetic factors that influence individuals' responses to exercise. Way back when we were, like I was doing this in the 1980s and 90s, we referred to people like as fast responders and slow responders, and this was because some people respond very quickly to strength training or cardiovascular training, where others can get there, but it takes them longer because of their genetic underpinnings. So, milestones in exercise science and physiology. So, to finish off, the discovery of lactate threshold and its relationship to endurance performance was right back in the 1920s. So, as lactate built up, exercise performance drops off, and very quickly you basically become fatigued. And we'll look at that in basic terms. If you really want to understand that, then physiology or biochemistry would be the subjects. We'll go into that in more detail, but it comes from the first part of energy production. Cellular respiration and glycolysis, where if you don't have oxygen, you're going to produce lactate as a result to keep the process going. But lactate is really lactic acid, and acid in any cell is not a good thing. 1950s, we saw the development of isometric and isotonic exercises. So isometric and isotonics, where you have the movements, and then you have the isotonic, where you have the same actual tone on the muscle, and isometric, where you don't move the actual muscle itself, but you just hold it in place. And these occurred in the 1950s, and both have a positive influence on the body. So again, we have, as has already been mentioned, the identification of genetic factors that affect exercise responses, and this kind of eventually paved the way for personalized exercise programs based on genetic testing in the 2000s. And to finish off, other significant findings include the role of glycogen in muscle energy metabolism, something that we will look at, the physiological mechanisms behind the runner's high, and the importance of resistance training for building muscle mass and strength. There's been lots of very interesting studies done even in the last few years on that, showing how fast protein intake through nutrition actually ends up in a muscle that's repairing itself. All right, well, thank you for listening to the first lecture. Yes, it went on a little bit longer than many of the other lectures will, but this is our introductory lecture, so thank you very much for listening.